A major feature of languages within the functional programming paradigm is the treatment of functions as first-class types. In other words, functions are not simply special entities defined in a specific syntactical way, but can also be passed as arguments to other functions and returned from other functions, just like any other type. The easiest way to demonstrate this is in Haskell. I've written here a function definition called myMap. MyMap is a higher order function because one of its parameters, f, is itself a function. The way that myMap works is that it will apply the function f to every element of its second parameter, which is a list, and the returned result will be a list with all the results of applying the function f. I can interact with this code and use several existing Haskell functions, such as absolute value. And if I apply myMap to that list, I get all positive results. I can also apply something like multiplication times 2, and the values from the list will be plugged in as the first parameter of this multiplication. And so when I apply this, I get the result of multiplying each of these values by 2. I can also use the round function to round a list of values that have decimal components. So this definition is fairly simple, and strictly speaking, the occurrence of f here in this case could be changed into an underscore because when the list is empty, it doesn't even matter what the function is. Now, interestingly, Haskell's type inference engine means you don't have to explicitly declare your types, but you can ask what the type of any function is, and Haskell will tell you. And what we're shown is that the myMap function takes as its first parameter a function from types t to types a, and its second parameter is a list of elements of type t, and its output is a list of things of type a. T and a are type variables that get mapped to specific types when you apply the myMap function. So when I'm using multiply by 2 as my function f, well, in that case, both t and a are arbitrary numeric types, because the function for multiplying by 2 is of type a to a, where a is numeric. If I'm using round, well, this is a function from a floating point value to an integer value, which means that float would be the t and a would be the integer in the type signature for myMap. That's why the input is a list of type t, or in the example I gave, a list of floating point values, and then the output is a list of integer values. Basically what map does is it takes a list of one thing, let's say in our example we're using the floating point values, and without changing that list at all, it creates a new list via application of the round function that has all the results. In fact, this type of operation is so useful that Haskell actually has a built-in function for it, simply called map. And map behaves exactly the same way as the myMap function that I defined for you. I can use map with multiplying by 2. I can map the round function. And if I check the type of map, you'll see that it's the same, although the specific names of the type variables happen to arbitrarily be different. Once you're used to the existence of these higher order functions, it makes it very easy to define other functions in a simpler way. For example, here is how you would define a function that rounds all the floating point values in a list without using map. You would have a case for the empty list that leads to an empty list, and otherwise you round the first element of the list and then recursively call round all on the tail of the list. This function works fine and gives us the same result, but I could simply define it in terms of map like this. Here the HO stands for higher order, and notice that I don't even have to specify the parameters. I could specify that there is a list XS and that I'm going to map the round function to that list XS. And if I run that code, it will work. But when you have the exact same parameter at the end of both the left-hand side and the right-hand side of a Haskell definition, you can simply erase it and get the same result. You can also return functions from other functions, and here is a simple example of that. This multiplier function will return a function that multiplies one value by whatever that one parameter was. So in other words, multiplier x returns a function that will multiply any other value by x. So I could call multiplier with a value 5 to create a function and then apply that function to the parameter 2 to get the value 10. I could also send my multiplier results to the map function. So I have a function that will multiply values by 10, and then I send that function as a parameter to map to multiply all the values in a list by 10. Another common pattern we see is that of taking a list and repeatedly applying an element to pairs of elements in the list, such as when computing a sum. If we're getting the sum of elements in an empty list, the result is 0. Otherwise, we take the first element and add it to the result of summing the rest. So I could call my sum on the list 1, 2, 3. That's 1 plus 2 plus 3 plus 0. In fact, this is equivalent to computing 1 plus parentheses 2 plus parentheses 3 plus 0, close, 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 and I get that result. Notice how the parentheses bunch up more on the right-hand side over here. This kind of operation is an example of something called folding, and because the parentheses are bunching up on the right, it is specifically a fold on the right side. In other words, there's a function in Haskell called foldR, and it can accept another function as a parameter and a base element, and if I send it the list 1, 2, 3, we'll see that we get the same result here. So foldR takes this plus operation, sticks it between elements of this list, separated with parentheses in the way we see there, with 0 as the rightmost element in the innermost parentheses. I can actually define a function this way. This is my sum higher order, and here I've explicitly declared the type of it because the foldR function can sometimes be picky, and Haskell might complain if I don't explicitly indicate that this is a function that takes a list of numbers and produces a single number. But that is the same definition that you saw me use in the code right there. And if I reload it, I can call my sum higher order on that list and get the same output. Now the type of the fold function is very complicated. It takes a function of 2 elements that returns a third. And notice that the inputs don't have to be the same type. In the case of addition, both my inputs were numbers of the same type, but folding is more flexible than that. B is the base element. In our example, it's 0. And TA is indicating that you can fold across things beside lists. And so we happen to be folding across a list, and so what we have is a list of numbers. but there are other data structures we could fold across that are designated by this foldable class. And then finally we have the result that we get out at the end. There is a corresponding fold function called fold_L for fold left, and if I were to apply fold_L to the same values, I would get the result, but that's only because with addition it doesn't matter what order I compute the result in. Fold_L is essentially computing 0 plus 1 plus 2 plus 3. So it's grouping the parentheses in a different order, which works fine for addition, but if you do this with subtraction, you get a different result than if you use fold_R. And I'll let you work out the details of that on your own. Though understanding how these fold functions work can be difficult, it is a very powerful way of defining many complex operations. In the previous video, I defined insertion sort as shown here. However, we can actually think of insertion sort as simply a fold operation on this insert function. So we have both this version of insertion sort as well as a higher order version of insertion sort. The insert helper function is defined the same way in both instances. And I can make this more explicit by removing it from the where clause and simply letting it be its own top-level function. So clearly, both versions of this code are using the same insert function, but the higher order version simply has to fold the insert function across an empty list. Once again, we will need to provide a type signature to make it easy for Haskell to interpret what is happening in this function. So what this type signature shows is that the elements of our input list have to be orderable. There has to be a way of comparing them using less than, etc. So we take one list of orderable things and output a new list. And of course we know that it should be the same elements but in sorted order. So the standard insertion sort did not use the fold function, and it gives us this result. But if I do the higher order version, I get the same result. Haskell has many other useful built-in higher order functions you can use, and as you write more and more recursive functions, you tend to find that most of what you would ever want to do can generally be encapsulated by one or more pre-existing higher order functions. And once you can see these patterns, it allows you to eliminate a lot of repetition in your coding. Common Lisp also has a large assortment of higher order functions, and what I've done here is define several of the functions we saw in the Haskell code using Lisp, in both standard recursive style and in higher order function style. So here is a function for rounding all the elements in a list using straightforward recursion. We check if the list is a cons. If it is, then we cons the result of rounding the car of the list to the result of rounding all of the cdr elements. Otherwise, we return an empty list. This matches a map pattern, and in Lisp there are several different map functions, and the one that's most analogous to Haskell's map function is called mapCar. The idea is that we keep taking the car of the list, as shown here, apply a function to it, and put all the elements together in one list result. Notice that the name of the function has both a single quote indicating that it is a symbol and a £sign or hashtag that makes it clear that it is a function. We can also compute a sum in Common Lisp, both recursively, as shown here, and using a higher order function that is similar to folding. The default behavior of the reduce function is actually somewhat similar to Haskell's fold left function. Here I have my list input, and my function symbol plus has the single quote and then the £sign to indicate that it's a function. I can also define insertion sort using reduce. First, we have the recursive version of insertion sort, which is the same as what we saw in the previous video. And then here is the insert helper function. And the higher order version of insertion sort will use the insert function, but we have some extra stipulations on how it is used. We specifically indicate that there is an initial value, which is the empty list. And notice that we didn't have to explicitly say that 0 was the initial value when using reduce for sum. And we also want to say that we're going to start from the end. This basically makes the reduce function fold from the right as opposed to folding from the left. So what you can see here is that Common Lisp's reduce function is a bit more powerful because it can do what Haskell's fold R function does and what its fold L function does. In fact, Haskell has 2 additional folding functions which have slightly different type signatures, and in Common Lisp, all of that would be handled by this one reduce function. But to make it behave properly sometimes requires unusually defined parameters like these. This colon syntax indicates a named optional parameter. So the default value of from end would be false, for example, but I'm saying I want to use t for true to make it be folding right as opposed to from the left. Regardless, there's a bit of code here at the bottom that tests this all out. We let the variable values take on this hard-coded list of values, and I both round all those values using the recursive approach and the higher order approach. I get the sum using the recursive approach and the higher order approach, and I sort the values using both the recursive approach and the higher order approach. And when I run this code down here, we'll see that we get the same result in each of those categories, whether using recursion or higher order functions. Though imperative programming languages are still much more popular than functional programming languages, many features of functional programming languages have seeped into some of the most popular imperative programming languages. For example, here is some Python code. Python has a map function. And if you import the functools module, then you can also have access to a reduce function that is similar to the Lisp reduce function and the Haskell fold functions. Note that I also import operator so that I can treat adding like a function, because if I were to simply put a plus here, that would result in a syntax error, since Python treats actual operators different from other function definitions. I test this code by printing the result of calling round all on this list and my sum on this list. And note that in the case of round all, which uses the map function, I also convert the result to a list. Python's map function returns a special type of map object, but if I want to simply see all the elements in order, then I can convert that to a list quite easily. Here is the result of running the code, showing you that it's straightforward to round those elements or to add all of those up to get this result. Even an old language like C, which is very imperative, has support for a few elements of functional programming. In C, one can define a pointer to a function. And if you pass that pointer in as a parameter to another function, then you have effectively passed a function as a parameter. That's a bit clunkier than how things are implemented in true functional programming languages, but powerful nonetheless. Here I'm defining my own map function. Now what I will do is take an array, although I'm actually using a pointer to the base element of the array, since this is a common way of passing arrays in C. And I also pass in the length of the array, since C arrays don't inherently know their own length. But what's interesting here from a functional programming perspective is this first parameter. This is a parameter whose type is a pointer to a function. The name of the parameter is func, and the type of the function is something that takes an integer parameter input and returns an integer. And so what I will do is repeatedly apply the function func to the input array, thus modifying that array to contain the result of repeatedly applying that function to each element. So I have a loop that goes through the length of the array. By using this pointer syntax, pointer array, this indicates a particular element within the array, and so I am replacing that element in the array with the result of applying func to that same element. And incrementing the array directly increases the offset where the pointer is in memory. So this is pointer arithmetic, which effectively moves to the next array element. Down here, I've defined two simple functions whose type signature matches the type required as input here, an integer input and an integer return value. Square takes an integer input x and returns x times x. Sub10 takes an integer input x and returns x minus 10. And down here in the main function, I have defined some test code. I have an array. I define f to be of type pointer to a function that accepts an integer and returns an integer. Length 7 matches this array here. First, I loop through to print out the array contents before I modify anything. Then I set f to be the memory reference for the square function. So this square is defined here. And then I map f to the array for those 7 elements. And then I print out the array contents again. Then I change f to be the sub10 function defined there. Map f again, and then print out those contents. So I can compile this, run the code, and we see that this sequence of elements contains the original array contents. These are the squares of all those values, and then from these values I subtract 10 to get each of these values. In the future, even if you do not make common use of functional programming languages, I hope that the lessons learned in this video will show you that you can apply functional programming style and thought patterns to other popular languages as well, which will often save you time and avoid unnecessarily repeating certain code patterns over and over again.